Hello. In this video, we are going to discuss the synthesis of amides, a carboxylic acid derivative. More generally, we are going to compare and contrast nucleophilic acyl substitution with nucleophilic substitution second order SN2. Here we have the general structure of a primary chloroalkane. Recall that chlorine is more electronegative than carbon, so this carbon-chlorine bond is polarized in such a way that there is a partial negative charge, and we do this by delta minus. Delta is the fourth letter in the Greek alphabet. And there's a partial positive charge on the carbon, which we show by delta plus. Now, because carbon has a partial positive charge on it, it is electron deficient, and therefore it is suitable for reaction with nucleophiles. Nucleophiles are attracted to regions which are electron deficient because they are electron rich. So we see that we can understand the basics of the reactivity of a chloroalkane or any haloalkane just based on the fact of knowing the electronegativities of the elements involved, and the fact that when we have a bond between two elements that are widely different in electronegativity, the bond is polarized, and the carbon in this case will end up becoming electron deficient and therefore subject to nucleophilic attack by a nucleophile. To the right, we have the general structure of a carboxylic acid chloride. And again, we notice that we have a single bond between an electronegative element, chlorine, and carbon. So we'd imagine that this bond is going to be polarized in such a way that there's a partial negative charge on chlorine and a partial positive charge on carbon. But notice something else here. We have another electronegative element, in fact, an element that is the second most electronegative of all the elements other than fluorine. So actually an element that's even more electronegative than chlorine, bromine, or iodine would be. So again, this bond is also polarized in such a way that the oxygen has a partial negative charge. So now the oxygen here has a partial positive charge, but we can intuitively estimate its magnitude as being even greater than the partial positive charge it had to the left, because in the haloalkane we have carbon attached to just one electronegative element. In the acid chloride, carbon is attached to two electronegative elements, and we have seen before when we look at the effect of electron withdrawing groups that the effects are cumulative. So having twice as many electronegative elements means an even greater effect on carbon. Carbon is even more electron deficient in the acid chloride than it would be in the chloroalkane. And since it's even more electron deficient, it is even more subject to nucleophilic attack in the acid chloride than it is in the chloroalkane. Now let us suppose that each undergoes a nucleophilic attack. So in the case of the chloroalkane, we have flow of electrons from the lone pair on nitrogen to the electron deficient center, while at the same time we have bond breaking between carbon and the chlorine, and we know eventually that chlorine is going to leave as chloride because chlorine is a good leaving group. An important feature is in the case of SN2, both of these occurrences occur simultaneously. So there is at one point in the transition state where nitrogen is bound to carbon at the same time that chlorine is still bound to carbon. So we have a pentavalent transition state, which is a fancy way of saying that there are 5 different groups attached to carbon in the transition state. 5 different groups attached to any one atom is very crowded, and we know that crowding around the electron deficient carbon in the transition state is a key director of how fast and how easily a SN2 nucleophilic substitution reaction takes place. Next, the acid chloride on the right hand side undergoes a nucleophilic attack, and we have flow from the electrons on the lone pair of the nucleophile attacking the electron deficient carbon. We also have the beginning of bond breaking between the carbon and the chlorine, and it's going to be heterolytic so that the chlorine leaves with the pair of electrons as chloride. We also have electron flow from the double bond onto oxygen. But here we see something interesting in the fact that when we get to the transition state for the nucleophilic acyl substitution on the acid chloride, we have a tetravalent transition state. We have 4 groups attached to carbon as opposed to 5. So clearly this transition state is less crowded, it's less sterically hindered than the case with the chloroalkane. So we would predict, we see 2 things in favor of the acyl substitution over the substitution of the chloroalkane. The first is a less crowded transition state. So we have tetravalent instead of pentavalent. And also we see that here we have 2 electron withdrawing groups, making the carbon even more electron deficient, so therefore more susceptible to nucleophilic attack, than in the chloroalkane, where we only have 1 electron withdrawing group. And we're going to look at these reactions in some detail and compare them to the results of electronic structure calculations, which will confirm our intuition that the energy of activation for the transition states for the nucleophilic acyl substitution will be smaller, in fact much smaller, than the energies of activation for the transition states in the case of the nucleophilic substitution second order, even when we have exactly the same nucleophile and exactly the same leaving group. Our first example will involve formyl chloride. So this is the acid chloride derivative of the simplest carboxylic acid, formic acid, reacting with ammonia as our nucleophile. So we realize that our carbon is electron deficient. So we have nucleophilic attack at the electron deficient carbon. We have bond breaking between the carbon and the chlorine, and the chlorine is going to leave as chloride. And we have flow of electrons onto nitrogen so that it becomes a carbon-oxygen single bond. This gives us the following transition state, which, as we predicted, is tetravalent. Carbon has 4 different groups attached to it. We get a separation of charge because now we have a negative charge on oxygen, and the flow of electrons from the double bond to oxygen. The ammonia comes in, and this has a positive charge. So we saw that we started with a neutral molecule, we added a neutral molecule, and in the transition state, we have a neutral molecule. In the next step, the carbon-chlorine bond is going to break. The electrons are going to flow from the oxygen back into the single bond, making it a double bond. That's going to happen semi-simultaneously. And then, right after that, this hydrogen is acidic. It's going to be abstracted by some base, which could be the solvent, or it could just be excess ammonia. So we're just going to put it as B, because we're not going to worry about the specifics of which base that it is. So we get our product, which is an amide, because attached to the acyl group we have ammonia. So this is formamide. The extra hydrogen from the ammonia here notice it's NH2 here, but it started as NH3. That remaining hydrogen is abstracted by a base, and then we have the leaving group leaving as chloride. So this is what happens in the synthesis of formamide. Now we look at the analogous reaction, the non-acyl version, where now we have nucleophilic attack of ammonia on chloromethane. And as we saw before, when we have chlorine attached to carbon, carbon becomes electron deficient. So now, during nucleophilic attack, we have simultaneously electrons coming in from the nucleophile, forming a carbon-nitrogen bond there, while simultaneously in a transition state we have bond breaking heterolytically with electrons leaving on chlorine as chloride. Merely drawing the transition state gives us some insight into how crowded it is, because we have 5 different groups attached, at least during the transition state, attached more or less to the carbon. So we have that pentavalent transition state. Then in the process of reaction, we have this bond breaks finally. So chlorine is going to leave as chloride. Now notice that if chlorine leaves as chloride, that has a negative charge. That would leave the remaining piece as having a positive charge. So what also happens is we need to abstract the solvent, some base that's present. We'll abstract one of the hydrogens from the ammonia. So we'll show that here. So that gets rid of the positive charge, and we're going to end up with a neutral product. And now we return to a tetravalent carbon, which carbon likes to be in neutral molecules. And we have a compound here which is an amine, specifically it's methylamine. And we have the extra hydrogen that was present in ammonia leaving with the base. Please see the following figures which show the computed structures of the reactants, the products, and transition states for this reaction, and before that, the reaction of ammonia with formyl chloride. Next, we look at the reaction of acetyl chloride. So this is the acid chloride derivative of acetic acid, reacting again with our nucleophile ammonia. In this example and succeeding ones, we're going to do it in a slightly more brief version, since we've showed it in gruesome detail for the reaction with formyl chloride. And we'll see that it proceeds almost exactly by analogy with the previous case. So we have electron deficient carbon. We have nucleophilic attack by the nucleophile at the electron deficient carbon. Electron flow on to oxygen, and we have flow of electrons from the bond onto chlorine as chloride. Then we have flow of electrons from the oxygen back into the single bond to make a double bond. we have the bond breaking that we started up there becomes complete, and then we have abstraction of the extra positive charge from a base. So when we had the separation of charge here, the negative charge that was on oxygen can be thought of as leaving with chloride, and the positive charge that was associated with nitrogen and this hydrogen leaves attached to the base. Therefore, our major organic product is going to be an amide, in this case acetamide, which is the amide derivative of acetic acid. We also end up with chloride and HB, but we're leaving that out because this is just to show the major organic product. Please see the following figures, which show the reactants, products, and transition state for this particular reaction and for the corresponding reaction of chloroethane, where we have the non-acyl analogous compound, to see what the reactants, products, and transition state look like in that case. Our third set of reactions begins with the reaction of propionyl chloride. So this is the acid chloride derivative of propionic acid reacting with a nucleophile ammonia. As we would expect, after the nucleophilic attack at the electron deficient carbon and the breaking of the carbon-chlorine bond and chlorine leaving as chloride, we are left with our major organic product that we'd expect, which is an amide propionyl, which is the amide derivative of propionic acid. Please see the following figures, which show reactants, products, and transition state for this particular reaction, and also for the corresponding reaction of the nucleophilic attack of ammonia on 1-propyl chloride. For our final set of examples, we're going to have the reaction of ammonia with butyryl chloride. So this is the acid chloride derivative of butyric acid. And now, as a self-test, you can pause the video and predict the major organic product. And then once you've come up with your answer, you can restart the video to see if you got the correct answer. Welcome back. The major organic product is going to be butyramide, the amide derivative of butyric acid. please see the following figures, which show the reactants, products, and transition states, their computed structures in the gas phase, as well as the reactants, products, and transition states for the nucleophilic attack of ammonia on 1-chlorobutane, which is the analogous non-acyl compound. Please see the two following tables. The first table shows the enthalpy of reaction and the energies of activation for the nucleophilic acyl substitutions, where we form the amides from the acid chlorides. In the second table, we are comparing the energies of activation for the transition states between the acid chlorides and the chloroalkanes. And the important thing to notice is that the energies of activation for the acid chlorides are on the order of 14, 15, or 16 kcals per mole, whereas the energies of activation for the chloroalkanes are 41 or 42 kcals per mole. So since the energies of activation for the acid chlorides are so much smaller than for the corresponding chloroalkanes, the reaction is much, much more favored, showing that substitution at an acyl group is far easier and occurs far more quickly than it would for the corresponding reaction for a chloroalkane. So again, we see not only the effect of the steric hindrance, but we also the effect of having the second electron withdrawing group, the oxygen, the carbon-oxygen double bond, that withdraws electron density and makes nucleophilic attack even more facile, easy to occur. Again, I thank you for your kind attention. Have a good one.